So today we're starting your last. Basically, I'm gonna start talking about analog and digital converters and digital to analog converters. We kind of already started talking about this with pulse width modulation last time, right? How you can actually grab and, well, you will. Wait, there's no lab next week, right? Yeah. When you come back from Thanksgiving, you will be able to basically, build a. I wouldn't. I started to say simple MP3 players, but like MP3 players are simple to begin with. So it's not even. It's just by definition, it's a simple thing. And you're gonna. I already showed you the code yesterday to do that. Um, but a lot of times, instead of having digital information and you want to just output it as an analog signal for a speaker for whatever reason, right? You want to go the other way, right? So you have some microphone, right? And then you want to record that information and put it on the computer. How do you do that? Okay. And this is where this class kind of culminate to what I like the most. And if you're going to go into experimental physics in the future, um, is based this will actually get you a position in a grad program. If not, you can actually go in industry and also get jobs dealing with this stuff. So the picture here is actually the detector I worked on when I was a grad student, called the compact muon solenoid. So some of you guys probably went to Dr. Veach's talk on the Large Hadron Collider. So this is the other experiment. Okay. We would say we're the primary experiment, but I think he would say he's the primary experiment. But we're competitors with each other when we were both trying to discover the Higgs in parallel to each other, and we actually both confirmed we found the Higgs at the same spot, which is a good thing. As opposed to, when you in science, a lot of times what happens is that when one experiment claims something, it's like, oh, did they really see it, right? But when two experiment simultaneously found the same thing, and that's a good confirmation that we actually did discover something new, as opposed to just looking at noise on the oscilloscope or something like that, right? Okay. So in this class, right, so far we have done analog stuff and with the digital stuff, right? What we're gonna do, right? The analog stuff deals with, signals of, all frequencies or certain frequencies, right? You can multiply them, you can divide them, you can do all that stuff with them, right? You can modulate them. Remember, we have to do that modulation stuff, right? For example, here, this is you can find this little modulation chip inside your modem. Don't break your modem apart to look for this, but this is basically the little multiplier chip that you guys put in when you did the modulation lab, right? And so analog electronics tends to look like this. It has resistors, has capacitors, and stuff like that, right? Where digital electronics, right, comes in these little nice square-shaped chips, right? These integrated circuits. These are mostly just logic gates or memory cells, right? D flip-flops pre-made already, right? And they'll output some, it converts it to decimal numbers, but the real output is actually in binary, right? Just like what you're seeing on your BASIS board when you guys are doing the counters this week, okay? So finally, we get to kind of combine these two together, and the two things we're going to be working with for the last lab is going to be the digital to analog converter. The short for this is DAC, the DAC, yeah, because DAC actually stands for something else also, with a Q. And then analog to digital, to converter, right? DAC and ADCs, okay? And this basically allows you to interface anything, maybe a science experiment, or maybe the antenna on your cell phone to your cell phone, right? Because your cell phone is actually a digital system, but the waves that the cell phone carrier is sending you is analog, right? Or, right, you talk into the microphone here. How does that get converted into a data stream that gets sent to YouTube or whatever you guys do with TikTok and stuff like that, right? Right? How does that happen, right? Okay. And we're also going to talk about how we can actually interface these devices with computers, right? One of the one of the first, um, these don't exist anymore actually, right? Wi-Fi cards. One of the first analog to digital interface is actually if you're, okay, so this still exists in your computer. Unfortunately, it's built in, so you don't actually see it. You can actually get the Wi-Fi signal through these antenna, and these antenna gives you the analog signal, and it converts it, right? So this part is analog, right? And then there's a analog to digital converter here that converts it to digital, like ones and zeros, so that your computer can actually understand it. So in case you guys haven't seen something like this, I can even just open one of these computers and show you guys. But this is a card that basically plugs into like inside your computer. So your computer is like this, right? You know, there's like a CPU here, right? And then there's these slots in the back. If you look in the back of your computer, you can actually see the outside of these slots. And one of these cards plug into it, right? And this is, in this case, this is a Wi-Fi card that upgrades your computer so it has Wi-Fi. But now basically all computers come with Wi-Fi anyway, so you don't really need to do it. Okay. And this digital system here, okay, is called instruction set architecture, or also known as ISA. Okay. So this is the older system, and more recently, people are using PCI, which is Peripheral Component Interconnect. These are just words that people make up to make nice acronym, PCI ISA. Okay. And the idea is that these interfaces are digital systems, so it only receives ones and zeros. You cannot plug your function generator into it and have it, you know, read out the signal. It has to do this analog to digital conversion first. Okay. Okay, there he goes. Okay. So these information transfer is purely digital, right? And if you're interested in how to connect, how to build your own PCI card, if you want, right? You can actually build your own. You can actually look at the pin listing, pin out information on Wikipedia, and then you can actually build it yourself if you want. Okay. And then you can connect it to the computer, and then probably the first time it'll be on fire, but next time it'll work, right? Okay. So, and this brings up a slightly different, unfortunately, the naming is so similar. This idea called data acquisition, okay? So data acquisition is a more general term compared to analog to digital converters and digital to analog converters. Data acquisition is, hopefully it makes sense what it sounds like. You have data, you acquire it, right? It's a system that allows you to bring some information and record it on a computer, right? Acquire that, okay? Okay. And in many experiments, and not just physics experiments, but also like in research or industry, you're going to need to record some sort of measurement, right? No matter if you're working at Intel, you're trying to figure out the electric field at some point in your FPGA or something like that, then you actually have to record that, okay? So your oscilloscope is actually a data acquisition. You just didn't realize it, right? Because these probes, right, wherever you place them, right, allows you to measure voltages as a function of time, right? And actually, if you stick in the USB here, I never taught you guys how to do that, but you can just stick in a USB and just have it capture information for you also. Okay, so inside your oscilloscope, okay, these oscilloscopes are actually digital systems because it does a analog to digital conversion. Okay, so these analog inputs, so this is maybe like channel 1, channel 2. You guys remember that on your oscilloscope when you back, what, like 4 labs ago when we did use oscilloscopes, right? Right, you plug that in, right? This gives you, you know, sines, cosine waves, so, you know, some analog signal, right? The first thing it does is it converts that to a digital system, a digital information, ones and zeros, okay, whatever that is, right? Maybe one that's longer or something like that. And once that information is digitized, so that's another key word, digitized, right? Then it can be, you know, manipulated with your FPGA, right? You can do multiplication, you can do addition, you can make it count, you can make it uncount, right? And then you can, you know, modulate it, you can do all kinds of fancy things. Unfortunately, you know, we only have 2 labs left, so we don't get to do a lot of different things, but But this FPGA basically, does all the logics for you, right? Okay, so you don't have to wire up 10,000 wires, right? Okay, right? And through this FPGA, right, you can store the waveforms, right? Just as I said with a USB, okay? You can output it, right? You can forward it. So there's actually a external output on your scope that can actually output this information also, okay? Or it can show it on a display, right? This is the actual picture that is drawing for you, maybe like 10,000 times a second, right? So that's what your oscilloscope is actually doing. So this is actually the schematic, right? The functional schematic inside the oscilloscope, okay? Um, and and of course, in order to change the voltage per second, voltage per division, and the second per division, there's some control, right? So these are all the control knobs that you're touching all the time when you're running oscilloscope, right? And this is actually what's inside your oscilloscope. It's a analog to digital conversion with a display system, okay? In other words, it's also basically have a 99% overlap with what's known as a data acquisition system, okay? Okay. So a lot of times you actually want to build dedicated, right? Um, dedicated data acquisition system as opposed to displaying something on the oscilloscope, sticking a USB drive in there, and then moving the data to your computer, right? So in experiments such as the one I was on, known as the CMS experiment on, right? What's happening is that, right, so I think you were out, maybe you haven't seen these talks, right? We're smashing protons together, right? Basically at the speed of light. You just accelerate them and then you smash them together and see what's inside, okay? Okay. The analogy that one of my professor when I was taking particle physics is that you throw one garbage can, you throw another garbage can at the speed of light at each other, and that way you can figure out what the hell is inside that garbage can, right? So that's the idea. And sometimes a little hit, a new particle comes out, and then you get to celebrate and get a Nobel Prize, right? But so what's happening is that you have a beam, right, of protons coming in this way. You have a beam of proton coming in this way, okay? And this is the interaction point, this green box in the middle. And what's happening is that those garbage is going to come flying out basically at the speed of light every 25 nanoseconds. Okay, you're smashing these things together every 25 nanoseconds. Okay, so what you need to do, these little green lines here are detectors, right? When a particle goes through here, it'll leave some energy behind so that you can actually detect that amount of energy. Okay, okay. We don't have to go into detail how this detector actually works. These are these are plastic scintillators. Okay, right? But this leaves a signal, right? So for example, if you read out this one, right? If I just plot this, right? This will be some pulse. These are called pulses that comes out. Okay. So these pulses get sent to a data acquisition system, right? And CMS, the data acquisition system, so these are the detectors. These are the little strips, right, that I'm drawing, the little green strips up there. Okay. Always forget what APV stands for. The first one stands for, the first letter stands for ADC. So it's an acronym of acronym, of course. Okay. It's like ADC pulse phaser or something like that. I don't want to remember what the V stands for. Okay. But what happened is that it basically convert that information, okay, right, into a light signal where it gets sent about 100 meters away, where that light signal gets converted into from analog to digital information, so that you actually have this ADC about, maybe like from here to the other end of Naragi far away in order to, because the problem is that these ADC is going to be big, because you need them to be very fast, okay? And we're going to see what, I'm going to show you what these boards look like, okay? So these ADC boards, you can even see the name here, Xilinx. Xilinx got bought by AMD, which uses Verilog, so that's why. That's why one of the reasons we choose AMD versus Intel is that Intel is more industry oriented, Xilinx more research oriented. So that's why I'm more familiar with Xilinx / AMD. Okay. So these boards, each of them about this tall. Okay. So you can imagine that you cannot fit like 10,000 of these inside a physics experiment, right? So that's why it has to be pretty far away. Okay. In fact, if we go back up here, right, right. So there are about 100 million of these strips inside here, so you need 100,000 ADCs, right? And then those wires go all the way out. I don't know if you can see with the projector here, these little blue racks, these are the electronic racks. So these wires has to come out here, basically go up to the roof, come back down, and go down here, right? Lots of cables, okay? Okay. And this is the motivation for the data acquisition system, so you can actually get information, okay? And these Xilinx ADC, these were designed in the 1990s, and it can send data at about 600 gigabits per second already. So a lot of times what happened in physics experiments, technology gets developed that usually, end user don't see for 20 years, okay? So for example, if you were, for consumer electronics, let's say you're buying a video card using PCIe, right? PCI Express 4.0. I think this is the fastest as of last year. Maybe it's faster now. I don't know if there's a new version of it now already. It can transfer things at about 6 gigabits per second, okay? So CMS that was designed in 1990s was about 50 times faster. But it has to be, right? Because you're smashing things together every 25 nanoseconds. It has to be fast, right? It's like playing a video game that has a refresh rate of whatever 1/25 nanosecond is, right? Right, at 40 megahertz refresh rate on the screen, right? Okay, as opposed to, what is it now? Like people use 120 hertz or something like that? 120, yeah, that's the standard now, right? I can't tell the difference, to be serious. 75 above, my eyes are too slow anyway. Okay, anyway, just to give you guys some numbers, right? So, like if you're streaming videos from Netflix, right, this will be about 15 megabits per second, right? So, so 200 megabits per second is like watching all the videos on Netflix at the same time somehow, right? Yeah, so this is like a ridiculous amount of data that comes out. For smaller experiments, which is the one I used to be on called Lux Zeppelin, instead of about 100 million channels, we read out about 300. Okay, and that's a small experiment, right? So this Lux Zeppelin experiment, so if you're interested in reading about it, only costs about $50 million, okay? Where CMS, right, remember, I don't know, Dr. Veach mentioned the cost of these experiments is about $10 billion, right? Yeah, it's like, GDP of like some countries, right? But they're, discovering new particles, so therefore, that's the price we need in order to learn that, okay? To confirm experimentally what a theorist actually think is happening, right? Okay. So I just want to show you guys some more pictures. So this is another type of sensor as opposed to a scintillator. This is a photomultiplier tube, right? And you actually have play around with a photodiode. It works on the same principle. For your photodiode, you need about maybe 10 million photons to hit it for you to see the signal. Okay, remember you get these calculations, right? This can detect a single photon instead, right? One photon hits it, you can see it. Okay. So if you actually have this on and you turn on the light, you actually break the thing. So just in case in the future someone asks you to turn on the lights while your PMT is on. Okay. And I just want to show you guys kind of what it looks like to design these systems, right? So this PMT actually goes through, the signal goes through two different, actually, it goes this way, the signal goes this way, okay? And then it gets amplified. Remember when we did amplifiers in lab 6 and 7, right? Okay, you can amplify it, okay? And then it goes through this thing called a DDC. So it's the digital digitizer converter as opposed to calling it ADC, right? It does the same thing, okay? And once this is digitized, right, it can be written to some computer disk, right? Then you can actually collect the data so that you can analyze it later, okay? Let's not talk about triggers and stuff like that, but because that's a little beyond the scope of what we're trying to do here, okay? If you want to learn more about this, join the EOS neutrino group because we're actually building the triggers for a muon detector, okay? Not, sorry, for a muon veto for a neutrino detector, okay? And so this is a picture of what the electronics board looked like on LZ. So this card, you can probably tell is about this big, right? And these are all little, they're SMA connector, but they're basically just smaller BNC connectors that are plated in gold, so they don't rust and stuff like that, okay? And each of these is like little FPGA chips that you're programming, and your analog digitizers here to convert all that stuff, okay? So we don't have to go through this in too much detail, just so you've seen some of these things, okay? So let's not. I really liked talking about this last year, didn't I? So yeah, there's a lot of stuff. So let's talk about how we actually can do this in our lab, right? So lab 13 is going to be an analog digital converter plus computer interfacing, just to kind of squish the two together so that you get kind of both experience, okay? Where we're going to get basically have the function generator give you some analog signal, right? You can make a sine wave, you can make combinations of sine waves if you want, right? You can put two together, right? Right? And so, you know, instead of a heart, we're going to use the function generator to make the signal, okay? And this comes in. We're going to convert it to digital, okay? And that's going to be done. There's basically there's an extra chip on your FPGA that includes this. So this is happening inside your FPGA, okay? And then you're going to send that data to your computer, okay? The computer your FPGA is hooked up to. So yeah, so this is the analog digital converter part of the lab. This is the computer interfacing part of the lab, okay? And this is why this series of lecture, I'm starting it this week, because it's going to take 3 lectures for me to explain everything, okay? All right. All right, so this is analog, this is digital. Hopefully that's good, okay? So why am I teaching you this stuff, right? One of the things that someone never told me when I was going to school is that most, unfortunately I'm going to talk about physics people, most physics majors don't go to grad school, in case you're wondering, okay? So this is a little pie chart. Oh, this is kind of old already, but so out of all the physics graduates with your bachelor's degree, just like what most of you guys are working on, or even you can just replace this word with science. I think even the fraction is even bigger on computer science, right? Because there's just so many computer science jobs. Right? 2/3 of physics students don't go into academics, right? They go work in industry, they become technicians who actually knows how to run an oscilloscope, how to use a function generator, how to do ADCs, how to program FPGAs to do stuff, right? You can work for Tesla and then program their little, you know, self-driving cars and not crash into pedestrians just because the moon is red or something for whatever reason, right? So all that interface between software and hardware, a lot of times either an electrical engineer is dealing with it or a physicist is dealing with it, right? Okay. So only 10%, well, 9% is going into academia, like, you know, people like me who, you know, just didn't want to get a job after school or something like that, right? Fields of employment, right, for physics graduates, most of you guys are going into engineering, right? So whenever you're graduating from here, right, some of you guys are graduating this year, right? When you look for a job, just because someone, you know, job says, oh, electrical engineer needed, right? You are qualified for that job, right? The reason they are posting that is just because, right, there's a certain set of skills they're looking for, and there's going to be engineering skill that you don't have, right, since you never took an engineering class where, you know, as opposed to making one experiment work, right, an engineer has to make thousands of products work, right? So that's a slightly different thing. A lot of physicists actually go into computer science, basically, and there's other jobs that happens, okay? Just to show you guys, right? So let's say you go on LinkedIn and you look for, what did I search for? Oh, analog and digital. I just I just search on LinkedIn the name of this class, right? And all these jobs comes up, right? Any senior jobs that's gonna require either like 10 years experience or a PhD, okay? So don't click on that, okay? But they're not seniors, right? Look at what their qualifications are, right? Profession in analog and digital circuit design, like you, right? FPGA, ARM, okay, so that's a different processor architecture, so but that's something you can learn. DDR, right? So you know about how memory actually work, right? PCE, so that's computer interfacing. A to D mean analog to digital conversion. D to A, digital and analog conversion, right? Fiber optics, unfortunately we don't get to do that too much here, but you can learn that on your own. So you have a lot of these skills already, okay, coming out of this class, especially if you take the next one, experimental physics, okay? And you know, this one does require a bachelor plus experience, but you could find one that, you know, doesn't have this experience thing, or just like a 1 year experience. And you can say if you get like a internship or something like that, you can call that your experience, right? Okay. Sorry to be kind of going off on this, so but hopefully I'm actually motivating why, you know, this class is actually useful. But okay, the point is that I want to get you guys to the point where we can understand how electronically, right, analog and digital conversion actually happen. Okay, so the goal is, right, let's see, did I put the, right, we have some analog signal. It doesn't matter what it is, right? It could be Wi-Fi, it could be cell phone, it could be my voice, right, a microphone, right? It could be the amount of light that's coming out of this room, right? It could be a camera, right? And this signal, I'm going to draw that in red, right? So let's call that A as a function of time. There's time, right? It's some squiggles, okay? Right? The idea is that, right, I want to convert this to digital information, okay? Digital information, okay, is going to be just a list of numbers as a function of time, right? So values, right? Okay, right? I'm not even going to try to do the binary version of it, right? Because I'm not going to be able to do the binary conversion quickly enough, right? So t equals 0, 1, 2, 3, 4, 5, 6. You know, this could be in units of nanoseconds, could be in units of milliseconds, whatever it is, right? Okay, right? So at t equal to 0, right, maybe this pulse is at 0. At t equals to 1, right, maybe this pulse is at 2. Right, at t equals to 2, it's pretty large, right? Maybe that's 10. At t equals to 3, it's down here, so it's equal to, I don't know, 7. Right, t equals to 4, it's pretty close to 0, let's call that 1. T equals to 5, right, it's pretty big again, similar to this, that's 10, right? And so on like that. Hopefully that makes sense, right? You're converting some analog pulse, right, into sets of numbers, right? That, you know, that gets, I mean, technically what's being read out is 0, you know, 1, 0, you know, 1, 1, 0, right? Trying to do all this conversion on the fly, right? So that's the goal, right? You want to convert, you know, this shape into ones and zeros, right? Okay. And there are various different types of ADCs, okay? There's the flash ADC, okay? This is what I'm going to cover today and try to finish, you know, not too much over, okay? There's a thing called counterseen ADC, tracking ADC. But what we're going to actually do the lab on is going to be known as successive approximation ADC, okay? And this is what most consumer electronics uses, consumer electronic uses. For example, your cell phone is using it, your computer is using that. The reason for that is because it's cheap. Okay? And I'm going to see why at least flash ADC is going to be expensive. Okay? So flash ADC is the simplest, but the most expensive. Okay? And we're going to see why. Okay? In fact, you can probably read about it on Wikipedia if you want. Okay? This is also covered in section 7.10, the last section on the PDF textbook that I sent you guys. Okay? Or that's available somewhere, right? Okay? How does a flash ADC work? Okay? Okay? Right? And the word flash, kind of indicates it's like fast, right? Okay? So this is a schematic diagram for a flash ADC to do 3 bits conversion. So this can go from 0 to 7, and that's it. All right? And so what's happening here is that you have a series of comparators, right? 1, 2, 3, 4, 5, 6, surprise, 7, right? Okay? Or not a surprise 7, right? Hopefully. Everyone knows why it's 7? All right? Okay? I'm sorry? 3-bit, right? Yeah, 2 to the 3 minus 1, right? That's the highest number you can output is 7, right? And you have a series of resistors here, right? All with the same value. There's no R1, R2, right? All have the same value. So this is an equal voltage divider, right? So let's say V reference is 7. Each of these will be in each step is 1 volt, right? This will be at 7 volt, 6 volt, 5, 4, 3, 2, 1. Actually, I think you have to start at 8, 7, 6, 5, 4, 3, 2, 1, and ground, right? Okay. Is there actually, I think, yeah. Sorry, not 7 resistors, right? 8 resistors, because you actually need one to break between this and the ground, but we'll see that, okay? All right, the input, right? Your microphone, your cell phone antenna, whatever it is you're looking at, right? Your PMTs, comes in with this V in here, right? And is connected in parallel to all these different comparators, okay? Okay. Okay. So in fact, what I'm going to do is I'm going to pick a voltage here. Let's say V reference here. I'm going to do that in red because then it's a different color. Just pull this up. I just want to make sure I'm using all the easy numbers, because otherwise the math will get a little bit interesting. Okay, so if this is 8 volts, right? This point it'll be 7, 6, 5, 4, 3, 2, 1. Okay, and I have a signal that's coming in, right? That is going from the maximum is 7, the minimum is 0. Okay, let's say it's something like this, right? Whatever, it doesn't actually matter what the shape is, right? That's what's being generated here, right? Okay. So what happened is that, let's say, right, at this point here, right, Vn is, let's say, 3 volts, okay? Right? Okay, if Vn is 3 volts, what's going to happen, right? This is going to be at 3, right? So all these positive side of your comparator input, right, is going to be at 3. And remember, the behavior of comparator is that if the positive is bigger than the negative, right, the output swings high. If the negative is bigger than the positive, the output swings low, right? Okay. So if, sorry, if the input here is 3, right, that means, okay, let's not say 3. Okay, 2.999999, just slightly below 3. Okay, because then this is kind of like we're not sure which one is higher, right? When you're comparing 3 to 3. Okay, but what that means is that this comparator, right, is going to swing high, and this comparator is going to swing high, but the rest of them are going to be low. Okay, no output from 0 volts. Okay. Okay. What happened is that when these are high, right, this is an exclusive OR, right? Sorry, this XOR here hopefully is readable. right? Okay. What happened is that this is exclusive OR gate. Okay. That means when the output here is both of these, the last two of these comparator, right? They're both outputting high. Exclusive OR of high high is 0, right? So that means connected to Q0. Q0 is basically going to be the ones place, right? So this is the, if you're writing a binary number, right? So this will be Q3, Q2, Q1, right? These are ones and zeros, ones and zeros, ones and zeros, right? Okay, so you get 0 as the output, okay? But up here, right, this is also connected to another exclusive OR gate, right? This output here is 1 still, so this is 1, but the one above it is 0, right? So this is exclusive OR between 0 and 1. But so that pulses an output of what? High or low? I'm sorry? Will be high, right? Yeah. So it goes through this diode. The reason for this diode is to prevent current from flowing backward. Okay, it just allows the current to flow forward. Okay, and now, right, this place is high and it has some resistor here, so it's actually holding this voltage at high. So now Q2 is actually 1, right? So Q0 is 0. So let's say Vn is 3, right? Q0 is 0. Q1 equals to 1. Q3, hopefully we can kind of deduce that since all these outputs are 0, Q3 is also going to be 0, right? Because Q3 is only connected up here, up here, up here, right? Okay, right? So the output is 0, 1, 0, which is equal to 2. Not quite 3. Right? Remember, I should have said this, right? Let's just make the output 2.9. Because when you get to 3, then it's like you're comparing 3 to 3. How's that, right? Okay? Right? All that works out? Make sense? You guys want to pick a number? It cannot be exactly an integer. Because then I don't know how to compare 7 to 7, right? Pick a number, and then we'll figure out what the digital output is. Just let's do one more example. Okay. Uriel, since you're falling asleep, pick one number. 7.2. Okay. All right. Okay. 7.2. Okay. So voltage input is 7.2. Okay. So what's going to happen is that, right, any comparator 7 and above is going to pulse high, right? High, 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 high. Okay. It's like you're going to a party. You have to say hi to everyone. Okay. So all of these are going to pulse high, right? But these exclusive OR gates going to give you 0, 0, 0, 0, 0, 0, because you're giving them 2 inputs of high, right? Except for this very last one, where the input, one of them is connected to ground, right? So that's going to make this exclusive OR gate send out 1, okay? And that's the only one that's 1, okay? And there's 3 diodes connected to it, right? 1 going to Q3. So I'm going to change the output of Q3 to be equal to 1. In fact, I'm going to get my mouse out of my hands. Okay. Okay. What's Q2 going to be? Q2 is going to be 0. Q2 is connected to here. All the way up here. Oh. Q2 is going to be 1. What's Q1 going to be? It's going to be 1. And 1, 1, 1 equals to 7. Not exactly 7.2 yet, right? But pretty close, right? So this is one thing that's going to happen when you do analog to digital conversion, right? You're going to get an approximate value of the analog signal. You're not going to get the exact. This is one of the reasons why people still play vinyl records. Did anyone do that? Vinyl record sounds better because your ears are just so good. You can hear the digitization, right? Because what's happening here is that when you convert this, right, signal from analog to digital, blue is digital, right? Instead of getting, exactly what the number is, you're going to get, 2, 3, 2, 5, 7, 1. So you're gonna like kind of pixelate it, right? Okay. So that's why, you know, music connoisseurs, they say, I don't listen to digital music, I'm too good for that. Okay. So since we kind of went through that exercise, just on the circuit, what I'm gonna have you guys, you're gonna see this in the homework. What I'm gonna have you guys do is I'm gonna do this kind of truth table thing. Should we just go through one of them just so you see how it's get filled out? Okay. So let's do 5.1. Okay. Okay. So 5.1, right? So what I want you guys to do is to actually figure out what the comparators are doing. Okay. C1, C2, C3. Okay, so 5 may be too high because we need, yeah, let's not do 5 because that's going to be too high. Okay, let's do, we already did between 2 and 3, so let's do 3.5, okay? 3.5, okay? So if the input is 3.5, right, that means this comparator is going to be high, this comparator is going to be high, this comparator is going to be high, right? So what I want you guys to fill out is that C1 is high, C stands for the comparator, C2, C3, right, high, 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 and this is X1, X2, X3, so the X stands for the XOR gate, okay? So what's the output of XOR gate number 1 if these comparator are giving you high outputs? 0, because it's exclusive OR, right? What about exclusive OR gate number 2? Back row, 0, okay? Exclusive OR gate number 3, what's going to be? Middle row. 1, right? So the digital value, well, okay. And I want you guys to propagate this forward, right? So now it's 1 here, 0, 0, right? So the only time, so this will give you a high value for Q2, right? And a high value for Q1, right? So 1, 1 in binary converts to decimal equal to 3, right? So the voltage is really 3.5, but you read out 3 instead, okay? Let's not do this reference divide by 3 thing, okay? That's just because we had a different voltage before, okay? Hopefully that makes sense. I'm gonna have this on the homework so you can fill these table out. So you actually kind of understand how these ADC actually works, right? Okay. The what? On the table on the homework, would it have whole numbers or would it be decimal? I'll give you the decimal. So, because yeah, that was not a fair thing that I typed into. Well, which one is bigger, 5 or 5? Okay. All right. Okay. So, right, this is kind of neat, right? This simple thing, right? Resistor, comparators, and an XOR gate, and a bunch of diodes actually, right? Just to protect the back current. So that allows you to convert analog to digital, analog signal to digital information, right? So, but it has a very high cost. You can already kind of see this, right? Right? A comparator is probably going to be like 25 cents, right? XOR gate, maybe 10 cents, even cheaper. A diode is 10 cents. You can see that to convert from, right, 3 bits, only 3 bits, right? It's going to cost you about like 10 bucks already, right? Okay, maybe not 10, maybe 5, 6-ish, okay? Right? In fact, right, if you count this stuff up, for n-bit conversions, right, the number of comparators and XOR gate you need is going to be 2 to the n minus 1 and 2 to the n minus 1 to the 2 to the 2 to the n minus 1 minus 1. Those are exponents, okay? I didn't want to try to simplify this using some StatMech stuff, but yeah, these comparators are maybe 40 cents, XOR gates 5 cents, diodes are 5 cents, so each of these is going to cost you about 50 cents. So if you were doing 10-bit conversion, right, so 2 to the 10 minus 1, right, so that's 2 to the 9, right, that is 512, right? multiply that by 0.5, right? Right? That's the cost of the comparators, right? And then the XOR gate and the diodes and the resistors is going to be similar in price. Okay, so basically it's going to be 500 bucks for you to convert a signal at 10 bits. Okay, and 10 bits only gets you up to from 0 to 5, not even 512, right? 510, 511. Sorry, yeah, because there's always a additional -1 here, right? Because you have to count the 0. Okay, right? So does well, I don't want to ask these days. Does your phone, right? Do you think, when the Google or whoever makes your phone, right, that when they make a microphone, right, they have to do at least 10 bits, right? It's probably like 14-bit audio actually they're doing. Okay. Do you think they're spending $500 to convert the audio, right? So hence, that's why they don't use it in consumer electronics. Okay. And I'm going to teach you guys how we can do this at maybe like 5% of this cost. Okay, so this is the fastest, okay, because all of this conversion occurs in one clock cycle, right? Now we know about clocks, right? Right. So if your fastest board is 100 megahertz, this conversion happens in 10 nanoseconds, right? Okay. In fact, right, applications for this, for example, if you're designing, this was declassified, I think, yeah, in 2001. If you're designing a ballistic missile that has to travel from, sorry, an anti-ballistic missile, okay? So if you had something that's being launched against you and you want to shoot it down in the air, right? Basically, the way you guide a missile is that, the missiles will have wings on it, right? And then whichever direction it sees the signature is going to try to point towards it, okay? But this has to be happening on the orders of micro or even nanoseconds, right? Because when the missile is traveling at about 25,000 miles per hour, a nanosecond is like a football field, right? Well, a microsecond is about a football field. Don't quote me on that. A nanosecond is still pretty short, okay? The missile will travel very far, right? So in order to get good guidance systems, right, usually the military will be using flash ADCs, right? Because that gets you the information fastest, okay? And this is why when you launch a missile, it's going to cost you like $10 million, right? Okay. Okay. In fact, there's these designs. These are like more engineering stuff, where a missile, has a thermal sensor system, right? It's just basically a light sensor, okay? What happened is that it goes through some optics, okay, where, it focuses the light and stuff like that, right? Just pretend it's like what's that called? Magnifying glass or optics, okay? Glass, okay? And it goes into there's a little control thing, but what happened is that, right, all that information gets fed into a complicated flight dynamic simulator and propulsion and synchronization and dynamic system that controls basically, where the fins are placed so that it can actually guide the missiles to the right place. Okay. So all these names are basically like, synonyms for what you're doing in lab 13. Okay. Without the 1 nanosecond timing, let's say. Okay. Okay, other places where you would find ADCs, flash ADCs, right, these fast ADCs, are, for example, in a neutrino experiment, where, where you have light sensors. Let me zoom out a little bit. Okay, we have a recent picture of this. This is actually a detector that's being built in UC Berkeley right now. Some of you guys seen this in person. Each of these little light bulb looking things is about this big, right? Right? So a person will be about this tall, okay? And what happens is that when a neutrino passes through it, it gives you a little bit of light, and that light gets detected by all these light sensors so that you actually know that the neutrino passed through. And what happened is that this light, because neutrinos are very, very fast, in case anyone ever asks, right? These pulses that you get from the neutrinos are going to be on the order of maybe 30 nanoseconds. Okay, this is another place where you need really fast analog to digital conversion. Okay, in fact, right, we buy these analog digital conversion card. So these are ADCs. They call them digitizers. Okay. Okay, and each of these costs about $20,000 for 16 channels. It can do 16 PMTs at the time, but so each channel is about, you know, $1,500. Okay, all right. So flash ADCs are expensive. Okay, here's a much better picture of a pulse. This actually came from the CMS experiment on one part of their detector. So you can see the time down here, right? Nanoseconds. This pulse goes up, and by the time, in like 40 nanoseconds, the pulse is gone already. And you need to basically measure this at multiple points in order to get this shape, right? If you don't get this shape, you don't know what happened, right? Okay, right. This brings up an interesting, what is it called? An interesting question. I wrote it down here, right? Is how fast can we do this conversion? Okay, right. Flash ADCs can do this in order of nanoseconds. Okay, right. And there is a limitation, right? Because, you know, in case you don't already know, right? Light travels about 1 foot per nanosecond. This is the one good thing about the imperial system, right? You don't have to memorize a bunch of stuff, right? 1 nanosecond is about a foot. Okay, so typically electronic wires inside stuff, they're about a foot long. Okay, to get anything that's faster than a nanosecond, you have to shrink those wires. It's actually the length of the wire that matters. Okay, but let's go back to this idea of sampling rate, right? Over here on this little plot, right? So this green thing is the reconstructed, right? Reconstructed pulse shape, and you know this black one, right? No one ever actually measured the black thing. It's just a simulation, okay? Because we can actually never measure anything. Well, you could, but this detector is designed to measure things down to the nanoseconds. Okay, it can digitize to the nanoseconds. So each of the width of these is 1 nanoseconds. Okay, I wish I zoomed in a little bit more. Okay, so come on, come down. Okay, so that means if this pulse, right? Let's just read it out for like 60 nanoseconds, right? That means you basically measure this pulse 60 times, right? In 60 nanoseconds, okay? That means the sampling rate should be what? 1 nanoseconds, right? So you're measuring the pulse every nanosecond, okay? I mean, you know, 1 nanosecond is much faster than that, but okay. So this is known as the sampling rate, okay? So this is unfortunately outside the textbook, right? But, right, for example, if you want to digitize a triangular wave, okay, there's the reason why the book, the textbook I got this out of, picked this example, right? Right, you want to sample for each period, so each period is just up, down, right? This is 1 period, right? How many data points do we want? 1, 2, 3, 4, 5, right? So for triangular wave, right, we want the sampling rate equal to, how should it compare to the period? I'm going to give you a hint and write t in a certain place. Do you want the sampling rate to be longer than the period or shorter than the period? Shorter, right? Because you want to sample multiple times per period. But in a triangular wave, how many times should we sample in a single period to get to know exactly what the triangular shape is in this example here. 5, right? So if you want something shorter, you probably want to divide it, right? So you want the sampling rate to be basically t over 5, the period of that wave over 5, right? That basically tells you exactly what the shape of the thing is, right? Well, unfortunately, not everything is a triangle. A mathematician may disagree, actually. So let's say we have a sine wave of 1 kilohertz, right? Right? If we sample slower than the frequency of the wave already, sorry, right? What's going to happen is that, so this black point is the signal that we're trying to digitize, right? These black points is actually the measurements from the digitizer, the ADC output, right? If you do it too slow, you can see that you're not going to realize you're actually sampling a bad thing, right? Because this still looks like a sine wave. Oh, okay. So in order for you to reconstruct, right, a pulse in general, right, what people usually use is they have this term called the sampling rate, right? So tau s, that's defined as the sampling rate, right? And then alpha is some number that's bigger than 1, right? Because what we're going to do, if, you know, the example I had before, right, we just had this alpha in the bottom, right? But this just removes the fraction of it, okay? Right? And this is period, basically the time of the pulse, okay? So a lot of times these are actually not periodic, so this is like the time of the pulse, okay? And they'll use this term, oh, if the time of the pulse is 30 nanoseconds, right? That means you want the sampling rate to be, you know, maybe 3 nanoseconds, okay? Because typically you want alpha to be around 10, okay? For just some general, okay, wave, okay? I mean, bigger alpha, the better, right? But, you know, bigger the alpha, the faster you have to do things, right? Okay? And that's going to cost, you know, shorter wires, more expensive electronics, and you don't have to deal with noise at that level also. Okay. So I cover stuff about why we're doing ADCs, how does a simple flash ADC work, even though it's the most expensive stuff, okay? What the sampling rate is about, okay? Next time, what we're going to do is we're going to talk about how we can cheapen this, so we can put it on our cell phones, right? That's going to be called successive approximation ADC, but in order for us to learn about that, we actually have to learn about digital to analog converters first, okay? And we'll see why, okay? Any questions? Stop.